I think that, thank you for the seminar. Everybody says it, but I'd have to say I end up watching some of them because I have some time meeting in the evening. I found myself on some Fridays evening watching the seminar with my kids. It was and they had fun, and I thought it was great that it was great to have a lot of the young scientists. Although I have to say I feel myself to be a young scientist, but I guess I'm not anymore. But that's what happened in life. Okay, so today I'm going to talk to you about the ice sheet, their contribution to sea level, also the glacier, and mostly based on the work that have been done with the GRACE satellite, the GRACE satellite mission. And I'm going to also, spend a few words talking about diversity, equity, and inclusion in science. And that's a subject that is very dear to me. And I've been spending more and more time for a series of circumstances, reading and being involved in various, thinking about it in the last almost 10 years. And it's been a learning process. And so I want to share some of my lesson learned and I think that, and then see what it goes. So I'm going to start. So here I want to show like picture of the group. This is like how we are. And this was before COVID. And the dog here, she's Grace. She was Iris when we adopted her, but she got confirmed to be Grace after the first day. And so I guess I'm very lucky to have some great people I work with, and I hope we're gonna get together soon. So far, we're doing a lot of things on Zoom. So the first things that you see, here we go. So I thought I'd start talking about, creating, how, creating a diverse and inclusive environment in science in the group. And I thought that that's a good, 2020 has been a really challenging year. A lot of things going on. It's been very special, and I'm trying to just see special with it. I'm thinking about this is like try to see what we can. I always, when there's something happen, I always say, okay, what is the good side of it? It's been a challenge in 2020, but I'm going to try to work on that. We had COVID. We've been in the house so long. I think I'm becoming socially awkward. And when I go outside, it's like, okay, what? We had fires, and we had, George Floyd and the Black Lives Matter movement. And I think that because of all this challenging, and because of the fact that it's been like so much going on, people really felt that, we were sick to be sick, it's too much. And so that's what prompted to have this strong reaction to, for example, to the George Floyd event. And I just would like to mention some of the, I want to share some of the, what I hear from is the provost and executive vice president of academic affairs at UCOP, Michael T. Brown, which is an incredible person. And when he talked, I was lucky enough to see one of his presentations, and he was saying, and he said, well, yeah, this year with all this going on, I asked myself, I saw what happened to George Floyd. It's like it's been happening every year. It's been keeping happening. What's different this year? And then he said, and then I thought, what it is that it's too much on top of COVID, on top of the fire, on top of everything. And so we, people have said, and so the next thing they said, which I thought was awesome, and then I tried to think, how can we look at this in the most positive way that we can? And I do think that to some extent, 2020 is an opportunity, because it's really created a momentum for people just be more receptive to change, be more receptive of what are things, what is like having an inclusive environment, having a place where we want to belong. And, and again, in addition to this, we have all, the election and everything is like, and so we have all those stresses. And so we should take this as an opportunity. I think, an opportunity to change, to keep the momentum and to engage people. And I thought that was really inspiring. And he also said, I've been trying to be as kind as I could and as positive as I could, because that way I can just, first is a way to get out of this cloud of, we had fire. We just it's like, we don't want to get bored, like this, like there are new things here in Irvine. So, need to figure out. Okay. So, I'm sorry, I was trying to trigger the timer, which has not been triggered, to make sure that I don't spend too much time. But now I have the pointer, so I cannot convert it. I'm gonna have to work on technology. Okay, so why are we talking about diversity? And the reason why we talk about diversity, so it's been, is because, it's really a practical reason. On one hand, there are many studies, and Fiamma a few weeks ago mentioned some of that, show that the diversity is really an agent, it just really drive excellent in team. Diverse team are very successful. And so that's one, of the motivation. On the other hand, also, we want to have, when we talk about STEM field science, we want to have our field and people that work in this field to reflect the diversity in our population. And if we look at that, well, we're not quite there. And this is a complicated, and it's it doesn't matter how we got there, but the point is how can we change this so that we reflect, what is what are the people around. So when I think about diversity also, I think that there is something that it comes out, and we're talking so much. I think in the last few years, there's been a big momentum. I mean, I think that everybody cares about diversity and inclusion, having a constructive and positive environment to work. But it is true that what does it mean? And being, aware of the need of everybody is not obvious. And so, but also, when we think about diversity, sometimes a lot of people think as a trade-off of excellence, but it's not. And so I think it's very important to think about this. The other thing that I think is very important to think is that diversity is not enough. If we have, diversity, but people, doesn't mean that we're gonna have excellence. The people together are gonna work better. We're gonna have this brilliant idea. The team is gonna be very productive. Because really we have to have inclusion. So people have to feel like, well, and in fact, if we have only diversity, it can even be counterproductive, because people feel like, okay, other, people don't understand us, as, if you're a single woman, among, and anyway, and so how do we create this environment then, help us to, what should we do? And I think that the key is that we really want to have, we need to have a very positive climate. We have to make people feel welcome, appreciated, make them feel that they belong, and have a support system. And that's not so trivial, because, we may mean, but because, and especially I think in our field, there's a big international, group, and they're people that have different, different culture and different, and so it's not, we have to really be aware of what make other people comfortable. And so I do think that it's very important, and I've been learning to just do that more and more. We have to listen to what other people need, observe, be aware, but overall is a work, is a cultural change. It's just change not to think based on what is usual to us, but just try to be more receptive and adjust. And I think that we all have to be very aware that, this process takes a lot of time. And the other thing is that we can have protocols, we can have procedure, we can have requirements that are required to foster this change. But we really need people to be ready to change and to be able to embrace it. Otherwise, the result is not going to be as effective. And so, how do we make this cultural change? How do we make people buy in? And that's a big challenge. And one thing so I do think there is a process that goes bottom up and top down. So we have to have a, a grassroots process. We have to have people involved. They're like the student, there are people, the really, and then we also have to have, the leadership. They could be, different level of leadership. Can be like the supervisor in a group, or, the chair, the dean, if we are, or the manager if you are in an institution. But it's really important. I think is very important. Has been, shown that like we need the support of the leadership. Also, we have to have accountability. We need to just think about, okay, are we doing the thing that we said we were doing? It doesn't mean that we have to have these humongous goals, but just have a plan and say, okay, did I do it? Did it work? And if it didn't work, that's okay, and just elaborate on that, maybe change the approach. I think that a lot of work is like becoming aware, and help people to be more aware. And that's a process. We are very used to just think, and even I do think that I think this community is amazing. We have some amazing people, but we are very aware, to think about what we feel. And what I learn a lot is that we really have to understand how other people feel, what is like, and again, that's a big lesson that, for me. Then we have to be inclusive, and also think about what we got from it. I do things that, people to buy in have to see what is the advantage. Why should I do this? And so try to, you do it because it's the right thing, but also why, and what is like the, what is coming back to us. So we should just be able to also show this to people. I think it's very important to have a goal. And so it can be at the institutional level, have a strategic plan, but set goals of whatever, what I want to do. I want to make sure that my students don't get stressed. And so how should I do? Can I put something in place so that, when the student that work with me, and I can reach out, or I figure out a way in which, and so they can be different goals, but having goal really help us to say, okay, this is what I'm working on. And then be aware of our implicit bias. And I do things that, we all have implicit bias. And that's what it is, because we all grow in a community. We have like whole a cultural background. We grow up in some situation. And so we are used all to go closer to what is more familiar. And that's okay. And I think the first step is like recognizing that we have them, and then pay attention and not make those implicit bias affect how we make choices and how we deal with people and how we set our environment. And so a good example, when I think about buy-in, I think those days, of course, we want to foster all those changes. And changes is always hard. When we are done doing, I think, even if we just really want to change. So there are a lot of, way in which we, of things that happen, they are, making us to embrace those changes to some extent. So now I say more and more job application, almost all, they require diversity statement. When I write letter for people, I'm asked to, can you please comment on the contribution to diversity, the potential of contribution to, to equity and inclusion of inclusive excellence of this candidate, which to some extent is a work for me, that I'm writing the letter. It makes me think. It's not just asking the person how to do it, but it somehow is a way to educate myself and make me think about what are those. And so I do think that we have all those approaches and those ways to look into this. And I think we should embrace it. And, I've learned a lot in all those years, and I'm going to try to bring some example along this talk. But, I have to, to really adjust. And I felt that more I paid attention and more I figured out there's a lot I have to learn. And I learned a lot for the student I work with and the people I work with. Okay, so let's go back to talk about science. And so this is a plot. So we have like two, on the top, we have 2 time series of the change, the mass balance of the Greenland Antarctic ice sheet measured from the GRACE satellite. Now, the subject of time variable gravity in its present form, it really started in 2002 with the launch of the GRACE satellite mission, because before we could not really do time variable vary with the application that they have now. And then when GRACE was launched, we had two satellites. They were like orbiting at about 450 kilometers. They were like in the 450 kilometers, and they are 200 kilometers apart. And they were like on free fall in the atmosphere, and they are subjected to the gravity, the attraction of the Earth. And so if we know exactly the position of the satellite and we monitor the change in distance, and honestly, this is pretty cool now, with the, they have a microwave link, the GRACE satellite, and, we can say the change to very high accuracy. And so we can convert those in what is the mass change that cause those changing, because we have the two satellites, and the first one get attracted by, let's say there's a mountain and accelerate it, and the distance become larger, and the second one eventually get closer to the Earth and accelerate, and the distance becomes shorter. And so, we know the position of the satellite, we just remove non-gravitational effect, and then what we do, we remove, the mean field, because the mountain is there every month. Those satellites can, cover the Earth. They have almost a polar orbit, 89 degrees of inclination, so they cover almost all the surface of our planet. And we can get basically a picture of the gravity field every month. And then if you remove the mean, we can see how much is changing from one month to the other. So we don't have an absolute, measure, but basically it's like we're weighing the Earth and whatever change in the monthly time scale. Turns out that, we remove the atmosphere, we know it well enough, using a global atmospheric model. And then we remove whatever are the signal they are sub-monthly using some, field, and there's an error in this. But after we do this, we are left with what changes at the surface, and what it changes from one month of the other. Well, I would say that, we have the water in the river basin, but the ice mass in the basin, on the ice sheet and on the glacier, that's what it changes. So here what we're seeing is like we put Greenland on a scale, and we are weighing this ice sheet. Of course, we have to figure out, some mathematical tool to extract the signal, because the satellite, we have some limitation in the spatial resolution, because the satellite are higher up at 450 kilometers of elevation. So we have a decay of the short wavelength. But here is a time series of the mass change of the Greenland ice sheet month after month relative to the mean during the entire period. And this is, and as you see, a lot of up and down, very regular, in the initial period, and then it just start to be less regular. And I'm gonna talked about this a little bit later more, but we have a big event of melting 2012, and then you can see again the big melting in 2019. And what this is like, I put together the three of the main solution. So there are different ways that the data are processed, and so we come out with different solutions, and they're in pretty good agreement. Actually, they match very well in Greenland, and so this give us, sense of the robustness of this result. If we look at Antarctica, we have way more variability, noisier, the signal. The signal is bigger. We have, again, once we get closer to the end of the GRACE period, again, GRACE was flying between 2002 and 2017. And then we had a gap, and which is the gray line here. And then we had the GRACE follow-on mission. So they are noisier closer to the end, because in 2016, one of the accelerometers failed, and so they had to adjust the way that they did the solution. But overall, they are pretty consistent, and actually this difference, and they generate consistent result. So I just want to quickly talk about the video, the animation down here. And what you see, this is the change in mass, basically starting from 2002, how the change in mass progress. And if you look at Greenland, you can see that basically slowly the mass loss spread, across the entire ice sheet. All the four sides of the ice sheet. It started more in the south, and then it expanded clockwise in the north, and it reaches also the northwest, and then it reaches the north. And this is consistent again with what we, with the fact that, what we know that is happening in the ocean as well. We know that, we have warm water that comes from the North Atlantic, and it just reaches Greenland. If we look in Antarctica, there's slightly different. We see the, basically the mass loss is localized in some area. We have, in this, like the pink area, the Amazon Sea sector, the peninsula as well. And then we have some pink also in the area of Totenmannsk and Wilkins Land. And then again, those areas, and then, we have some, those area, a whole area where we have pinkish, or area where we know the, the ocean, the ocean water is warm, and it corresponds to area where we have, the warm water is carried by the Antarctic circumpolar current. So let's zoom in on Greenland. And so we said that the two mission, GRACE and GRACE Follow One, and they were not overlapping. Ideally, when we have satellite mission, we really would like to have an overlap, because we are sure that we have continuity in the data. But that did not happen. And so how do we, one of the first things that we looked at when we looked at the data was like, can we just figure out, do we have continuity of the data, and can we figure out a way to fill the gap? And so to do this, we used some independent data, and in this case we used the data for the mass budget method. Those are like combination of surface mass balance minus ice discharge from measure and observation ice bridge, ice thickness, and from Eric Rignot and Jeremy Mougineau. And so what we did, we said, okay, let's look at this. And then we just said, okay, let's, that's correct, line up the data. And during the grace period, we made the trend of the MDT change from the mass budget agree with the one from grace. And really what we wanted to do, we wanted to see if we have consistent in the time variability. And if you see, they agree pretty well overall. And so this can be really ask, confidence in the data. And again, the difference, this is like a constant, change in the FTT is really is caused, is basically this offset is uncertainty in GIA and correction for grace, and which is a constant DMDT, and uncertainty in absolute ice discharge and absolute SMB in the mass budget method, which is another constant. So we evaluate the continuity, again, at the scale of the entire ice sheet, and then also at the regional scale, in sub-region. And here, one thing that we just see, I feel like we see that the mass loss was changing quite fast, pretty regularly in the, again, initial period, but then after, in 2012, we start to have this, record melting, which is repeating himself in 2019. And so we have two very, extreme of record melting in a very relatively short period. And, and then between them, we have a relatively, some colder, some relatively slowdown. And what we are observing is actually consistent with what we know from what the model, the climate model predict in terms of the impact of the circulation in the Arctic, and the blocking effect. So, which is like, so if we look at the entire Greenland ice sheet and we look at the sub-region, so we divided the ice sheet in this big region. They're still big enough, but they are characterized by different, how the mass, the characteristic of the loss and the precipitation. And so we see that most of the signal mass loss is coming from the southeast and for the northwest. But also, and those are like high precipitation area. We have, again, a lot of, a significant component also from the southwest. And here is mostly the mass loss is due to melting, but still all the way to the north, we have, we have a change and any decrease, an increase in mass, a mass loss of the ice sheet. And actually is quite significant. Is about, more than, is about 42 gigaton per year if we combine the north area. So I guess exciting, if we look at the ice sheet, is an exciting time because things are changing and they're changing fast. So let's move to Antarctica. And Antarctica, slightly different story. If we look at Antarctic ice sheet, again, we have the variability is changing. We have basically much larger variability. We have two big bump. We have like in 2006, a bump, and then again in 2017. Most of the mass loss is coming from the Amundsen Sea sector, and lost my mouse. I'm not sure where I put it. Let me see. Okay, here we go. The pad mouse. Okay, the Amundsen Sea sector, the peninsula also, but the Amundsen Sea sector is really like 4 times as large as the peninsula. And then if we look also the combination of, Totem, Moscow, and Vulcan's land, we just have, we sum those two components, we just get comparable with what is the, the mass loss that's coming from the peninsula. And we have some area of where we have, again, some gross cycle coast, Quimor land as a consistent, the mass loss there started in 2009, looks like it was slightly slowing down in 2014. And then it picked up again after that. And overall, we are seeing also the bump in 2017 is a combination of what is going on, in the peninsula again, and of the consistent change in Quimor land. Now we don't know if this is going to be a long term, but so start is persisting. Okay, so this is another, and I'm going to browse through this relatively, quickly. So we look at the ice sheet, we look at big region, and now we can also zoom in at the basin and sub-basin scale. And here I want to point out one of the, I think, application how we can use GRACE. So it's a very powerful in determining the mass balance of the entire sheet. It gives a monthly measurement, is a comprehensive measurement, but also we can use it to evaluate regional climate model, and surface mass balance. So this is some work that, so what we have a limitation of the resolution of GRACE, but this is because the shorter wavelength dim faster. But if we have, a region with a very localized and a very strong signal, we are able to define what, I call here mass count Taylor optimized solution. There are solutions for which we solve in a specific region and we extract the signal. And as long as we have an high enough signal to noise ratio and we can limit the leakage, we can extract the region in a smaller area. So in this case, this is an example for the Totten and Moscow University. And what we did, we created, a solution or an averaging kernel. So we extract the signal associated with this three mass, this three circle, the three mass count. And also we use the entire basin. So if we look at the entire basin, we're not able to say, can we say which one? So we use the mass budget method. There was using, in one case, the Fluxys plus MAR and RACMO 2.3P2, which here is not reported in the figure. And in another cases, using RACMO 2.3P1. And what we find, if we look at a big area of the basin, we are not really able to say which one of the time series of mass loss agree better with GRACE, but once we zoom in a smaller region in the sub-basin at the front of the basin, we can see that when we compare the mass balance calculated, using MAR or using RACMO, we can just say that, the one using MAR is not consistent with the GRACE data. And again, we try to be very conservative about error, and I can answer questions about that. We did this in a couple of other regions, the Amery sector, and then GATS. And the idea is like we can define the solution in places where, we can have advantage in evaluating model, their remote section. But this is like a powerful way to evaluate the surface mass balance model at the regional scale. Okay, so I didn't plan about talking about the glacier, but after Richard Alley talk last week, I thought, we should, I should just bring up. So one of the things that we can do with GRACE, and I think that is very valuable, is that we can look and use this data to evaluate, to estimate the glacier and ice cap mass changes. And again, this is like, so what we did, we used a method and we adjusted that was developed initially by Jacobs et al. This is work that is led by Enrico Ciraci, which is was a student in our group, and now is gonna be going to do an MPP postdoc. And what we did, we look at we use the random inventory. We look at all the global glacier and ice caps. We define mass count solution to extract the signal in those areas. Here are the glacier. And we found that basically 7 regions, they're covering about 94% of the total glacial area, are accounting for about 90% of the total mass loss. And those 7 regions are here. They're like the Canadian archipelago, Alaska, Southern Andes, Iceland, Russian Arctic, High Mountain Asia, and Svalbard. And they are, again, this is, is a comprehensive measurement. We cannot zoom on a single glacier, but at the same time, we have a way to evaluate, what is the evolution at the regional scale. And that's important because, again, those glaciers, in addition to contributing to sea level, especially in areas like the Southern Andes and High Mountain Asia, are key to water resources in highly populated regions. So what we know that there's a lot of interannual variability here. So how do we, so what we did to look at the, at the continuity and try to fill the gap, we use MERA to surface mass balance data. And the idea is that, the glacier, most of the mass change in the glacier is mostly dominated by surface mass balance. And what we did, we took the MERA2 data and we calibrated using GRACE. So during the GRACE period, we made the change in mass of the cumulative MERA time series agree with GRACE, and this is an absolute offset. And physically, what this means, this physically tells us is a reflection of if we did not account for the ice discharge, that's a component of the mass loss, that's going to be part of what is going to be reflected. But otherwise, this is like this offset is basically accounting for the model bias. And here is like the offset varies. In a few cases is large, but usually it's not terribly large. And it's actually pretty impressive how well. So those time series, the color one are GRACE and the dashed line are the time series of the MERA2. SMB. And if you see, there is like an excellent agreement. I actually was surprised myself. And so this has been useful both for, again, data continuity and filling the gap, but also shows us how we can use GRACE to evaluate the model at the regional time case. Again, if we look at the contribution from the Arctic, to the total contribution of the glacier ice sheet, this is about 69%. And they account for the 65% of the glacial area. So if we sum all the ice sheet together, we are getting about, this is the time series, and we get a change of about 280 gigaton per year during the entire GRACE period. And here is a map of the trend. And so mostly of this signal is coming from the Arctic, but again, it just give it, so we can just put together this signal with all the other one. And I thought that's like, and we can say, okay, what is the, and look at what is the land ice contribution to sea level. And again, all this work that has been done as shown here, has been done by, there is a contribution of many people of the group. And Joya is working on looking at the sea level contribution of, of the regional variation of the sea level due to those contributions. So if we sum all of them, we have about 1.8 millimeter per year of sea level. And if we compare it with the total sea level during this period, which is about 3 millimeter per year, we have an idea of what is the potential, contribution of the land as a cryosphere. And then also I want to point out the sum of Antarctica and Greenland, the ice sheet is overpassing the glacier, the glacier contribution. Okay, so the last things I'm going to talk about is some work that I'm doing with Sarah Kapney at GFDL. And, so observation, so GRACE is an amazing tool. We have amazing observation. And I think we are, I just really think it's the golden age of remote sensing. We have GRACE, so GRACE follow one. We have mass budget that combine, information from fluxes for interferometry. We have altimetry. And so we have all those observations that monitor different aspects, that have different uncertainty, and they have different strength for monitoring the ice sheets. But eventually, to make projection and to see what's going to happen, we're going to need model. And so here is some work that we have been doing to use GRACE to evaluate those models. And in this case, this is some work that we've been doing with the Sarah Kapning at GFDL to evaluate the GFDL. This is like the atmospheric land couple climate model, and using the GRACE data. So we've been working, and now the model output a variable that is the equivalent of what GRACE measured, which is the total water storage. And what we did, this is an example, we extracted the signal in the region, this is like high Montanesia, in 2 sub-regions of high Montanesia. They're big enough to be compatible with the GRACE footprint. And those regions are like, so the green one is the, the Western Himalaya, which include the Karakoram, the Kulum, and is an area, the Pamir, is an area that is highly influenced by the westerly and the monsoon. And then we have this blue area, where's the Himalaya, which is the area from which we, we expect and we just observe most of the glacial mass loss. So what we did, we extracted the total water storage from GRACE. So we did not remove, in the estimate that was shown before, we are removing the hydrological signal outside the glacier area using a hydrological model and GLDA, CLM. In this case, we took the entire signal and we compare it with the GFDL. And if you see in this area, in the Western Himalaya, we have a pretty good agreement in the interannual variability. But also we see we're missing. Sometimes we don't get the the minimum during some year. And so, and then, if we look at the Eastern Himalaya, the Himalaya per se, the area from which we expect to have more of the glacial mass loss, we find that, well, the GRACE has a bigger trend, as a consistent, mass loss during the period, why the model doesn't see as much. Or now in this area, most of the, so now we can go back, and I think the key for doing this is really working with the people that run the model, because we have to understand enough of what are the process, what is the parameterization to try to interpret this. And the idea is not just to evaluate the model, but also do it in a diagnostic way. Can we provide feedback so that the modeler, can, adjust, some of the parameterization or check some of the assumption. So for example, in this case, which by the way, I also want to point out, the high Montanesia are a key area because they are like very important for water resources for a highly populated area. And at the same time, because it's one of the most challenging area, we have a large, we don't have a lot of very reliable observation. The model are challenged because of the elevation, the big changes in elevation. And so what we find in here, we find that overall, the model is doing pretty well. And then we just step back and you say, does it tell this about the processes and about the model? Well, it turns out that the model does not have glacier melts. And so what it means, if we do pretty well and we capture the interannual variability, it means that in this area, most of the change we are observing during this period can be, is driven by the atmospheric, circulation. But why are we missing, the mass? Why the model doesn't see this mass loss, in some specific year? Well, it turns out that if you have a very warm year and we have some ice melting, so the model does not have that component. And so, this, so the Italy process is like, when we have a very warm year, the model can only melt the snow that comes during that year. And so if there is additional melt, GRACE see the effective loss. And similarly, we can look at this in the Himalaya, and here where we have a consistent year after year, like the trend tells us that there is the glacier melt is happen consistently. And what we find that the model doesn't capture this. Now, the important on this is that, overall, we are able to evaluate those models at the regional scale. The GRACE provide an integrated estimate of the total water storage, and is a conserved mass, which is key to evaluate in the model. And so it's really a very important tool if you want to just improve the model and trying to evaluate where, but again, it takes work, and then work with people. The model is not just like, oh, I'm evaluating and I'll give you back feedback. And so I'm very excited about this work, and Sarah does, the GFDL, they're doing some great work, and Enrico and Geruo, in our group, are working with us. So the last things I'm going to show is this plot. This is another evaluation example of using the GRACE data to evaluate the winter snow product from the GFDL models. This is like atmospheric land model. And what we did here, we said, so one thing that we want to think about when we think about the model is like, we have to think about what is the variability of the signal that we want to evaluate, and in time and in space. And so here we said, okay, we have total water storage, but if we just look at the mean change in winter of total water storage at the location of a glacier in ice caps, and and we just look at and extract this signal, this should correspond to the change in solid precipitation, and so give us information about how the model represent the solid precipitation, so the snow product. So what we did at all those locations, we extract, we process the data, we remove the high frequency and the noise, we remove the trend, we look at the mean change in the winter precipitation, December, January, February in the north, June, July, August in the south, and then we plot the one from GFDL and GRACE, and they agree pretty well. And when they don't agree, usually there are areas where we know that there is, basically the variability, there's region that have the greater disparity, they have more precipitation bias, and the error are standard deviation between the two. So this was the last thing that I want to show, and I'm just gonna put some conclusion. And I think that, what we want to, to take home, from the, I think that, the glacier and the ice sheet are melting fast. I think that that's a great opportunity. Maybe it's not good, but it's a great opportunity for all of us. When I started, and many people start earlier to work on ice sheet and glacier, it was not as exciting. I mean, it was exciting, but now it is really meaningful, and we have a lot of implication of what we're doing there, like both for, if you want, for not just understanding the physical process, but also the impact that this understanding has on making decision on availability of water resources, on regional sea levels, so impacting coastal area. And so we are in a good place. Then the other thing that I think we should think about, while 2020 has been very challenging, we should just really take, just try to see, the positive. And every time I try to see the positive, something more happens. So I'm not complaining anymore. But I do think it really created a momentum. I think that, it gave us an opportunity to create community in a different way. And so let's try to see how we can leverage on that. And in terms of diversity and inclusion, I do think that, this, I think that we have a change, the trend as it changed, an increase of momentum, like in the year, and then given the situation of this year. But, we have to really, when we want to increase, I think it's very key, because we really want to have a good place to work. And that's what, at the end, a successful place to work. But we have to understand the challenges, we have to listen, and we have to engage. And, we need, short-term and long-term goal with accountability. And that's okay if we don't meet those goals. but that helps us to not, to make sure that we are moving in some direction and we're making progress. And then, I think that like in science, the process is a slow process, and again, we may not get it right enough, but I think that, I guess is very rewarding, and is just, I don't know, I find that, and still like, it's okay. It's just good to try and do the best that we can. Okay, so now I'm just gonna, so we have, because given all the example that we had, we did something. We have a debut of our group, and this is like the, oops, does it work? It's not working, that's not it. Okay, screen. Oh, it's sharing the screen. Okay, screen, white screen, pointer. It would be great. Okay, so does it? No, I don't want to end the show. Well, I don't know how to start the movie independently.
You could just unshare the screen, start the movie, and then share that.
Yeah, about that, exactly. That was too fancy. You see, I hope the movie is there. Okay, so this is like, and we kind of had fun, and thank you to everyone. Let's see if, can you see the screen? Oh, it doesn't work on full screen. Whoops. It's not working on full screen. Oh yeah, it does. Okay, there we go. Okay, so did everybody? No, we're Jean is practicing now.
Oh, great.
Do you have the lyric, Jean?
Yeah. Yeah.
We can do now. We can do a couple of times now, guys.
Oh my God.
It's okay. It's okay because we're all singing, so it's not gonna be clear what's going on.
Oh my goodness, I'm terrible at singing though.
That's good. That's good. Like Ryan, you are one of the ones that knows how to sing, so we want to hear you for sure. You see, that we're trying to mix.
Yeah, you have to cover my voice up.
Yeah.
It's now time to make a change. Just wake up, roll your sleeves. You're so young, you're so brave. There's so much that you can do. Find a goal, make a plan. If you want to graduate quickly, look at us. We do science and we're happy. We were once like you are now, and know it can be tricky to stand up, speak your mind, and feel welcome to the team. Take your chance, don't hold back, think of everything you can give, for we need you tomorrow with your feet at home. How can I make her afraid again? Stop the melt, clean the air, the trees, touch the sun, and make all the people change. From the moment I decide to make a difference, I discover it's so cool to be part of it. So cool to be part of it. Okay, and there we are. Okay, so
Ready practice.
did everybody? It's gonna go in loop. I don't think you want it in loop, but, and I have to say thank you for the AGS because we did that, and thank you to these amazing guys because they came with me along this adventure and singing, and I love it. I think we're awesome. I'm sorry. Okay, and I think I'm done, and I'm ready for any question. But
Okay, fantastic. So there was a question on the chat a little while before the, Julian, do you want to unmute yourself and make sure that question is answered? Julian Williams?
Hi, can you hear me?
Yeah,
yes.
we can. Yeah.
Okay. Hi, I just wanted to ask, does the high mountain Asian area, does it include the Tibetan Plateau?
So those two areas that I showed did not include the Tibetan Plateau. The Tibetan Plateau, let me go back. Let me just go back here. No, I didn't miss. Okay, the Tibetan Plateau would be like this yellow area. And actually, we did a comparison here too, and we found with this model, the first run of the model did not work very well in the Tibetan Plateau. And then what they did, they changed the vegetation and some of the, the hydroclimate that was changed as a consequence. And now we are in a good agreement between, but this does not. So this is basically, this green area correspond to this time series, and the blue area correspond to this.
Okay, thank you, and excellent choiring.
Yeah.
Roger, do you want to jump in?
Yes, hello, and thanks very much, Isabella, and to your team. My first question was one of your very first slides. You remarked that Antarctic data were noisier, and I wasn't sure whether that was you were just commenting on the fact that your plot for the Antarctic and for Greenland covered very different ranges, and therefore whether the noise was actually the same in both, or whether the Antarctic is fundamentally noisier signal, and if so, why?
So, okay, so overall, I think that the variability in Antarctica, because we have more variability, we do, okay, let me just go back. I can go back to this, so just to this one, which is...
Yeah, that's the one.
like, anyway, so there. So I think that overall there is, so it's also part of the error, but, there is more variability. So the Antarctic overall is, is very, but I think particularly what I would say in addition to that, so there is, closer to the end of the grace period, we do have a noisier signal. And you can see it even more in, like when you compare the different solution.
Okay,
like,
so it's not some fundamental thing about the satellite orbits all being close together over the poles, or anything to do with satellite processes. Thanks.
No, here is due to the fact that late in 2016, one of the accelerometer failed. And so the solution is done using a single accelerometer. And it turns out that because of the pitch of the spacecraft, this kind of, had an effect on the noise of the solution. And so.
Okay, thanks. And the other part of my question was probably unfair because it was just a general thought about the difference between the measured 3 millimeters a year sea level rise and the 1.8 contribution that you've elegantly and carefully calculated from the mass loss.
Yeah, so I guess you should ask when it has like, yeah, it was like, is a stretch, it's clearly is a how do you say, provocative, but I just like, if I put it all together and assume that everything goes straight into the ocean, which is not what's happening.
Sure.
And so that was like, but I think that to me was like order of.
Yeah, it was as much a passing thought as anything else. So thanks very much for the presentation and your answers. Cheers.
Is there anyone else with a question? I'm really delighted to see that, Lauren, you're actually there with a team, or a room full of people.
Yeah, that's actually very cool.
Any further questions for Isabella?
I should just not go on the movie. What is like the picture of the team, of the dog would be the best one to leave things on.
Any more questions? It seems like that might be all the questions. So I guess,
Well, I mean,
is there another question there? No, it's still Rogers. So I was just going to advertise next week's seminar, which is hopefully coming up. Oh, hopefully that's. So hopefully there's advertisement for next week's seminar, which is 3 shorter talks from early career scientists. So hope to see you all next week. So thank you very much again, Isabella, and thank you to your team. And thank you to the multiple Erics that attended the seminar. We were very impressed. Okay, so thanks very much to everyone, and see you next week, when I think the US will have changed time, but we'll still be in the same time zone. So it'll be presumably back to where it was before, I think.
Yes, you will. Bye, Tari.
Okay, bye, and thank you very much, everyone.
Bye.
Wow, we did it. I thought we were shot.
No,
That's
it
great.
wasn't their fault.
No, well.